Welcome. This is a talk for the ICCV 2021 workshop on unsupervised 3D learning in the wild. In this talk, I'm gonna go through 3 research works of my group, GRAF, Giraffe, and Campari, which all tackle the problem of 3D-aware image synthesis from just unstructured and unposed image collections as input. This is joint work with my PhD students, Michael Niemeyer and Katja Schwarz, and with my postdoc, my former postdoc, Yi Liao. As we all know, generative models are fantastic. And the idea behind them is quite simple. We sample a latent code from a low-dimensional latent space. We pass that latent code to a generator, which is a complicated nonlinear mapping that's parameterized by a neural network. And this outputs the data sample, or a sample that looks like a sample from the data set. And here are some samples that are generated from StyleGAN 2. It's amazing how well these models work these days. Here you can see models or pictures from cars generated from this model. And if you sample more latent codes, you get more different generated images that all look like cars. But is generating photorealistic images all we need? In this talk, I want to argue that there is something else that we'd like to have. As for many applications, we also require control over the image generation process. For example, when creating animation movies, we need to control the actors in the scene. Similarly, for video games, we even hand over control to the player of the game. So we clearly need to control very precisely the game content. And similarly, in virtual reality. So what we'd like to have is a generative model for 3D-aware image synthesis, which allows us to first generate photorealistic images, but also to control individual objects, for example, with respect to their appearance, pose, and size in three-dimensional space. And we also like to control the camera viewpoint in 3D. And ideally, we'd like to train these models without explicit supervision on these latent quantities. We'd like to train them from unstructured and unposed raw image collections. Now, this makes this problem really hard. The first question that we need to answer is, what representation should we actually use for 3D-aware image synthesis? And there's a couple of options that have been explored in the literature. Platonic GAN uses a voxel-based 3D shape representation. They take the latent code and they have a 3D decoder that generates a voxel grid with RGB color values that are then rendered into an image using a differentiable but deterministic rendering function. The advantage of this approach is that it is by definition multi-view consistent, because the rendering function doesn't have any parameters, and we have a single 3D shape representation. But this approach has quite low image fidelity, as you can see here, and due to this voxelized representation, high memory consumption. An alternative is to, and that has been presented in ICCV 2019, it's called HoloGAN, is to sample a 3D feature volume. This is also a voxelized representation, but the voxels don't comprise color values and densities, but they comprise features. And then we have a neural renderer that is now a parametric mapping that takes this and projects it into an image and transforms it into RGB color values in image space. The advantage of this method is that it produces higher fidelity images, but because of this neural rendering function that is learned, it often entangles object shape and identity with the viewpoint. And so if we now take images from the same latent code but different perspectives and try to reconstruction doesn't look very good. So in GRAF, we presented the first work that used radiance fields, like in NERF, in the context of generative models. Was basically trying to build a GAN for neural radiance fields. So the idea is we sample a latent code, and then we condition a generator, a radiance field G theta, on that latent code, and that radiance field, which is a MLP, a multilayer perceptron with parameters theta, takes as input a view direction and a 3D location and outputs the color value and the density. And then we render this using standard non-learned, non-parametric volume rendering. Now this gives us a continuous representation that's by definition, because we don't have a learned renderer, multi-view consistent, as you can also see here on the right by the reconstruction. If we take our model and generate multiple images from novel viewpoints and reconstruct that back using CalMap, we get relatively clean reconstructions. And it also leads to high image fidelity and has a relatively low memory footprint due to its neural implicit representation. Let's look at this model in a little bit more detail. We start by sampling the camera matrix K, the intrinsic parameters, the camera pose Xi, which are the extrinsic parameters, and a patch sampling pattern nu, which is illustrated here on the left. We need the patch sampling pattern as it's very time and memory consuming to render an entire high resolution image using a radiance field representation. And so we only render patches like a patch gun. And then we compare these patches to patches of real images using the discriminator. Next, we pass the intrinsics, the extrinsics, and the sampling pattern to the generator G theta, which samples corresponding pixels and rays based on the sampling pattern. For each ray, like in NERF, we get the viewing direction dr and the sample points, 3D points along the ray, as illustrated here at the bottom. And then we push this view direction and the 3D points through a positional encoding, as illustrated here, and use them as input to a conditional radiance field. And we call this a conditional radiance field because it's conditioned on additional latent shape and appearance codes, CS and CA. And then we pass these two as a condition to the conditional radiance field, which outputs then the color and the density for that particular point and a view direction. And then we use standard volume rendering as in NERF to render the color values of the predicted patch P dash. In order to compare this patch to a patch from a real image, we sample a patch from the real image using the same sampling strategy that we used here. In this illustration, the patches are of size 5 by 5 pixels, but in reality we use 32 by 32 pixels. The advantage of using this fixed patch size of 32 by 32 pixels is not only that it's faster to render, but also we can use a canonical, standard, and shallow 2D convolutional network as the patch discriminator. So this becomes now very lightweight as well. So the key idea here is to build a generator and a discriminator for image patches of size 32 by 32 pixels, where these patches are sampled at random locations and with random scales using dilation, as illustrated here, such that we cover all areas of the 3D volume, all rays, and also all pixels in the reference images that we compare against. Let's have a more detailed look at the architecture of the conditional radiance field. This is this orange box here. Similar to NERF, we use a fully connected MLP G theta with ReLU activations. And what we do is we inject the appearance code CA as well as the view direction information later into the model. such that they only influence the color value and not the density. And the advantage of this is that it introduces an inductive bias which allows the model automatically to disentangle shape and appearance. This graph model has two inductive biases. The first inductive bias is that we force the entire generation process of the image, unlike StyleGAN, through a 3D representation. And the second is that we use specialized architectures which have inductive biases to disentangle the latent properties that underlie the 3D scene. Let's look at some results. Here are results on the synthetic color dataset at 256 pixel resolution. Despite the fact that we don't input geometry information, this model automatically recovers and gets a sense of the depth of the objects. So here's a false color coding depth map. So we automatically discover geometry, otherwise rendering of the appearance wouldn't work as well. You can see here what happens when we change the viewpoint or the appearance or the geometry or identity of the vehicle. Here's an example on Celeb A HQ, also at 256 pixels resolution, where you can also see how from this data set also depth maps have been recovered. Now this was for data sets which were relatively simple, where we had a dominating object in the center of the image, and this was an underlying assumption of how the data set was created. Now, of course, the question is, can we scale this idea to more complex multi-object scenes? So the key contribution of GRAF, as a reminder, was to incorporate a 3D representation as an inductive bias into the generative model. Now in Giraffe, we incorporate a compositional 3D scene representation into the generative model. And in addition, we now use a neural renderer that yields fast and high quality inference, which means we're giving up on multi-view consistency, but we're gaining a lot in terms of rendering speed. And that was actually crucial to make this model work. Let's go through the model step by step. In Giraffe, we sample N shape and appearance codes first from latent shape and appearance representations or distributions. And from those, using a neural radiance field, a conditional radiance field representation, we obtain N feature fields. This is now, unlike graph one feature field, now we have N feature fields which cover each individual object as well as the background. Note that here we show features in RGB color for clarity, but what we do instead, and what's different from graph before, is that we don't sample the color and the density, but we sample features and densities. And the advantage of doing that is then, if we project these features into the image domain, we can render smaller images, which is faster because this radiance field volumetric rendering step is the slow component of the algorithm. So we can make that much faster by rendering just very small images and then applying a 2D decoder that upsamples these small images to full image resolution. As a next step, we sample the size and the pose for each of these feature fields. You can think of these little cubes as having a local coordinate system so that we can stitch the scene together. And so we get a staged scene as illustrated here with the background and these two objects. And then we compute the composite of all these feature fields, of these posed feature fields, which yields a single 3D scene representation. Again, these are just features, but illustrated for clarity as RGB here. Then we sample a camera pose, we render the low resolution feature image, and then we upsample that feature image using a 2D decoder, using this neural renderer to a final high resolution image. And of course, that's only possible because we have rendered features here which comprise more information, where the model can leverage these additional channels to upsample with to higher resolutions here. At test time, We sample individual codes to control shape, appearance, and pose, as illustrated by the red dots here, which yield a novel 3D image and a novel 3D scene that can be rendered into a 2D image. As already mentioned, we volume render the features at a very small resolution. In practice, we use only 16 by 16 pixels, which makes the approach very fast and therefore allows training, and upsample this via decoder to a higher resolution, say 256 by 256 pixels. And therefore, unlike GRAF, we can directly train with an adversarial loss at full resolution. We don't need patch-based training, which in this case doesn't work so well with this disentanglement requirement, but we always need a full look at the scene, so we can now train using this idea of a low resolution feature projection directly on the entire image resolution, because this part here is fast and this part here is now also fast. As conditional radiance field architecture, we use the same as GRAF, but we simply replace the color head here with a feature head. So going from 3 dimensions to a higher dimensional space. Scene composition works as follows. Given n feature fields that are represented in terms of the density and the feature value for each of these fields, and they can be evaluated at any continuous location in 3D space and for any view direction, we combine the densities by summation and the features by a density-weighted averaging. This is a very natural way of combining volumetric representations. Let's have a look at some results. So here we compare our method on the right against a standard 2D GAN on the left on the task of object translation. And as you can see here, the 2D GAN isn't able to fully disentangle the different latent aspects of the scene. And when you translate an object, sometimes also the identity changes, or the color or the appearance changes, while we in our approach can modify precisely one component only. We have full disentanglement and we can translate independently of the object shape or color. We can also perform more complex operations like circular translations, which are impossible with a 2D GAN, because the 2D GAN is not able to disentangle translation from the other factors. We can also add more objects at test time than the model was trained with. In this case, the model was trained with scenes comprising only 2 objects, and we are adding more objects at test time. We can also rotate the object. Note that for this dataset, the dataset is very biased. It contains a lot of views, frontal views and back views of the car, and also side views, but less views from angles in between. And so we get a little bit of this bias also in our reconstructions here. We can also translate the object, and we can change the object shape. On the left, you can see examples for cars. On the right, you can see church examples. We can also change the object appearance. So these are the different latent codes that I've shown you before. This is now changing only the object appearance. And we can even generate out of distribution samples. So here we are translating the car to locations where it hasn't been observed in the training set. Or here we're adding more examples to the scene. Here's a comparison of rendering time. If we would render a full resolution 256 by 256 pixel image using GRAF, using a neural radiance field directly, this would require us about 1.5 seconds. In comparison, however, the feature rendering at 16 by 16 pixels plus upsampling works at 5.9 milliseconds. So the scene-based neural rendering and upsampling yields fast inference. One thing that I didn't tell you about is that for all of these previous approaches, as well as all the approaches that were appearing concurrently at the same time, typically assume that the camera distribution, the viewpoint distribution, is roughly known. And how this is done in practice is that you look at the data set and you adjust, for example, the elevation and the azimuth angle distributions of the camera such that they roughly fit what you expect the data set to be like. And if you don't do that, then you get very distorted results. The model doesn't learn properly anymore. So this is not nice. This is a lot of manual hand engineering. If you talk to the people that work with these models, if you talk to my PhD students, they'll tell you, oh, I worked a lot on getting these distributions right so that my results look good in the end for each particular data set. And of course, we'd like to automate this process. So the question is, can we learn the camera distribution as well? Yeah. As a comparison to GRAF and Giraffe, where we learn a 3D-Aware image generator from unposed image collections, but which require careful tuning of camera post distributions. Here in Campari, which has just been accepted at 3DV, we learn a 3D-Aware image generator and a camera generator jointly. The idea is super simple. We first sample a prior camera from some camera prior distribution, and the parameters that we sample here include the intrinsics of the camera and the extrinsics. In particular, we parameterize the intrinsics by the focal length and the extrinsics by putting the camera on a sphere, looking inwards at the center of the sphere, and we're parameterizing the camera then by the radius of the sphere and the elevation and the azimuth angle. So now we're sampling these parameters from a simple uniform-like distribution, and we feed that into a neural model, the camera generator, to transform this distribution into the desired target distribution over camera poses. And then we feed this into our 3D-Aware image generator, which is similar to GRAF and Giraffe, except that here we just consider one background and one foreground object. And then we have a discriminator that discriminates the generated image from a real image in the dataset. Let's look at some results. What we see is that Campari indeed learns to match the ground truth distribution for these data sets that we consider. So here on these data sets, we actually know the distributions. We can control the distribution of camera angles on these data sets. In this case, we plot only one of these dimensions, the elevation angle in degrees. And here the ground truth distribution has 4 peaks, has 4 modes. The initial distribution is quite uniform here that we're using. And it's iteratively, during the process of training, transformed into a multimodal distribution here in green that resembles the true underlying camera pose distribution in orange. Here's another example where we transform the blue from the blue to the green distribution. And this indeed makes a difference. If we use the uniform distribution, not the hand-engineered distribution that the PhD students chose, but we choose a uniform distribution, then the models don't work very well. So what we see here on the x-axis is that the object should actually rotate, but the object doesn't learn properly, the appearance is distorted, and the object doesn't rotate properly. But in contrast, when we use our model that also learns the camera distribution, we get nicely looking shapes again that also rotate according to the latent code. That's all for today. In summary, we propose novel methods for 3D controllable image synthesis. We've demonstrated training from raw, unposed image collections. We incorporated compositional 3D scene structure into the generative model, and we gain explicit control over individual objects during synthesis. In future research, what I believe will be important is to scale these models to larger and more complex multi-object scenes. While we are already able to handle some level of complexity in the results that I've shown you, we are far from handling the complexities of random images in the real world. Also, we believe it's important to enhance photorealism. There's still quite a significant gap from our models to, for example, 2D GAN outputs like StyleGAN 2. And I believe we will be able to see methods in the near future that are able to close this gap. And then, of course, we want to also disentangle other quantities, for example, quantities that concern physical light transport, such as lighting, materials, and so forth. That's all from me today. Thank you very much for listening. If you're curious about our research, I can recommend you to have a look at our blog. Thanks.